All right, here we go. This is the last of our energy videos. So today we're going to get two topics in here. We're going to do a little bit more about work by variable forces and kind of tie that in with our work kinetic energy theorem. And we're also going to talk about power, the rate at which work is done, the rate at which energy is transferred. All right, so remember, anytime you've got a variable force, if your force is changing, we can't just do work equals force times distance, right? And I guess I should comment here, most of the problems here are going to occur just along an x-axis. So for most of these problems, we won't need to worry about the cosine theta part. And pretty much all the examples here are going to kind of jive with that, where all of our motion is going to be along one axis. All right, so anyway, again, if your force is changing, we can't use this equation, and instead you need to take an integral. All right, and one of the things we learned earlier, somewhere in this giant chunk on energy, is that to calculate the work done by a force, you integrate the force with respect to the position, okay? And then conversely, if you know the work being done and are trying to find the force, you can take the derivative of the work, and that'll give you the force. Now, let's see if we can tie this in with the work energy theorem that we were working on, earlier this chapter. All right, so what we learned earlier this chapter was this, that the change in kinetic energy is caused by, your net work, done by a net force, right? And so with that in mind, to calculate the net work, we can integrate the net force, okay? And again, conversely, you can go the other way. You can calculate your net force by taking the derivative of the net work, okay? And notice, because work is a change, you can just replace the net work with the change in kinetic energy, okay? So you can differentiate your kinetic energy with respect to position, and that'll give you your net force, all right? The other thing I should point out here is there's no negatives to worry about here, right? Maybe I commented on this in the last video, I guess I did, but there's no negatives, right? If you want to do change in potential energy, that's equal to the opposite of the work done by conservative forces. And so when you integrate it, it got ugly, right? Here we don't need to worry about any of that because the work done by your net force.
Mark Trumkovich, if you're in the building, could you please come to the auditorium? Mark Trumkovich, please come to the auditorium. Thank you.
Well, now, Mark Trukovich, I hope you're doing well. All right. Cool. I guess that's all I need to say about that. No negatives to worry about. All right. So let's dive in and just do an example. And I'm actually going to do two examples. The first example I'm going to do is going to use this idea of integration. And then I'm going to talk about power. And after I do power, I'll come back and do an example with differentiation. Okay, we got to take a derivative. Okay. So anyway, here we go. So some mischievous, which incidentally, mischievous, this is spelled correctly. You guys don't care, but I'm going to tell you this anyway. I thought that was how you spell mischievous, but it turns out it's not. It's mischievous, which I guess is probably just pronounced mischievous, right? So this, not even a word. Mischievous, not a word. Mischievous. There you go. How's that for your AP Physics? All right. So anyway, so some mischievous squirrels have set up a number line along an icy tree branch. A mouse who has a mass of 0.5 kilograms is sliding to the left at 4 meters a second when he reaches a position of 0. So at x equals 0, our velocity is -4 meters a second. Okay. At this instant, the squirrels begin to exert a variable force. So we've got this team of squirrels, and they're all working together, and they exert this variable force. And the magnitude of the squirrel's force, or not the magnitude, the actual force, I probably should have put a little vector hat on this because the direction is indicated there. So the force that the squirrels exert is given by 8 plus 2x minus x squared. Okay. And so the question wants to know, when the squirrel gets back to x equals 3 meters, what is his velocity? Okay. So we're going to use the work kinetic energy theorem, right? We know enough information to figure out his kinetic energy, right? So his kinetic energy initially is going to be 1/2 of his mass times his velocity squared. So that gives you 4 joules if you calculate it. All right, so if we can find the change in kinetic energy, we can use that to find the final kinetic energy, right? Okay, so here we go. Let's see. Whoa. So let's see. KE final minus KE initial is equal to our change in kinetic energy. That's equal to the net work being done. Net work being done is equal to the integral of the net force with respect to position. Now we're finding the integral of net force with respect to position. So our position is going from 0 to 3 meters, right? We want to figure out how much the energy changed between those two positions. All right, so this becomes the integral from 0 to 3 of, well, the squirrels are the only force, or I guess the force of the squirrels is equal to the net force, right? Because presumably gravity and normal force will cancel each other out. So we want to integrate 8 plus 2x minus x squared dx. So let's see, the integral of 8 is 8x. The integral of 2x is x squared. The integral of x squared is 1/3 x cubed. And then we want to evaluate between 0 and 3. Okay, so let's see, if you plug 3 in, you get 8 times 3, which is 24, plus 3 squared is 9, minus 1/3 of 3 cubed is also 9. So that's if you evaluate 3, minus if you plug in 0, you just get 0. Oh, so this turns out to be 24 joules. Okay. Oh, well, that is this, right? That's this. So let's see, KE final minus, remember our initial kinetic energy, oh, I'll write it out. KE initial equals change in kinetic energy. So for us, KE final, we don't know. KE initial was 4 joules. We figured that out when we started the problem. That's got to equal our change, which is 24 joules. The worst J in history. So that means that KE final must be 28 joules. So now we can find our velocity. The mouse's mass is 0.5 kilograms. Don't forget your square root. And you get about 10.6 meters a second. Okay? There's one other thing here that I guess I should probably comment on, which is this. So at the beginning, the mouse is actually moving to the left. So I sort of glossed over this a little bit. I don't know that I really want to go into it because I don't know that I see a thing like this showing up on an AP test. But I am assuming here that our force remains positive long enough to get the squirrel moving back to the right so that he will, in fact, get to this position, all right? So that might not be a bad idea for you to investigate a little bit, to kind of look at, you know, I guess just convince yourself that he does, in fact, turn around before the force becomes negative, okay? So, and we can talk about that in class if you guys want. Just remind me, all right? Okay. All right, next example, or not next example. All right, so next topic, rather. Power. So hopefully from honors you remember that the power due to a force is the rate at which that force does work, the rate at which it transfers energy from one form to another, or from one object to another, or whatever. All right, last year we talked a lot about, well, not a lot, but we talked a little bit about calculating average power. Okay, so average power is exactly that. You're saying, all right, I did this much work in this much time, so if I divide, I find out how much work I did per second on average. And because of that, the units for power are joules per second, and we call a joule per second 1 watt. Okay, So notice, be really careful here. Power is measured in watts. Work is measured in joules, all right? And unfortunately, the two W's don't go together. That always messes me up, so just watch out for that, okay? Power is watts, work is joules. Okay, now, in the same way that, like, we know that average velocity is displacement over time, right? And instantaneous velocity is the derivative, right? So, right, because you're looking at how much the position changes over an infinitely small time, right? So same idea. If you want to find instantaneous power, you differentiate your work with respect to time. Notice now we're differentiating with respect to time, not with respect to position, right? So this is the main reason I grouped these two together, because I want to call attention to this distinction. dW dx is force. dW dt is power. Please, please, please watch out for that distinction. Okay? So let's see. So if power is the derivative of work with respect to time, watch what we're going to do here. We're going to replace work with the equation for work, right? Force times displacement times cosine of theta. Well, go brain. Yeah, so if we're looking for instantaneous power, well, you're going to have some instantaneous force, and then we can kind of change, look, this is delta x, right? So we want, that's the thing that's sort of changing, right? So we can rewrite this as f cosine theta dx, right? Because as you move, it's your position that changes, right? I guess your force is changing too. There's really a lot going on here. But anyway, this works. You'll learn more once you take more calculus. Okay, so, oh, and look, as we said just a second ago, dx dt is v. Okay, so it turns out that you can calculate your instantaneous power by doing fv cosine theta, in other words, by taking the dot product of your force and your velocity, instantaneous, right? So if your force is changing and your velocity is changing, you can still calculate your power by taking a dot product. Okay? So, let's do a real quick example here. This is, I think we did this one in honors last year, so I'm going to kind of plow through this. So it says, Roy lifts a 20-kilogram box up 3 meters in 4 seconds. Assuming the box began and ended at rest, how much power was used? And I probably should have been more specific here. By Roy. Okay, so the power that Roy uses is, well, that's the same as the work that Roy did divided by the time it took. And notice this is just giving me an average, right? In the same way that, you know, if I said it moves 3 meters in 4 seconds, the best you could do is find an average velocity. Similarly, the best I can do is find my average power. Okay? Well, Roy is a non-conservative force, right? So that means the work he does contributes to a change in total energy in some amount of time. What type of energy is he giving the box? Oh, he's giving it GPE in some amount of time. How much GPE? Well, that's mgh, right? So let's see, the mass of the box is 20 kilograms, 9.8 meters a second squared, mg times h. What did we do? Lifted it 3 meters, and this took 4 seconds. So if you multiply this all out, you end up getting 588 joules worth of work that he did in 4 seconds. So that's 147 joules per second, or 147 watts. Okay, so that is actually the average power that Roy used, 147 joules per second, 147 watts. Okay, and then just to make sure you're clear with what a watt is, it says how much energy will a 60-watt light bulb use if left on for 12 seconds? Well, just do dimensional analysis, right? 60 watts is the same as 60 joules per second, right? So in 12 seconds, we're going to use 720 joules worth of energy, right? In terms of your equations, it's this. Power is work over time. That's the same as the change in energy over time, right? So our change in energy is power times time. 60 watts, 60 joules per second, times 12 seconds. Okay? All right, so those were sort of honors grade problems. Let's move up a notch, all right? So sometimes the power generated by a force is not constant, right? We talked about that a minute ago. And in that case, like I said, you can calculate the power by doing the dot product of your force and your velocity. All right, so in this example, Roy's going to push a 30 kilogram box from rest across a, it doesn't say, but a horizontal frictionless surface with a horizontal force of 120 newtons for 5 seconds, okay? So part A wants us to find the average power. All right, so for part A, let's see, P average. Well, that's the work that we did divided by the time. So to find the work, I guess we could find the displacement, right? So we could do, there's two options here. We could either do force times displacement divided by time. So I'd have to figure out how far it moves. Or if we assume that's the, you know, that Roy's force is the net force, you could find your change in kinetic energy and divide that by time. And either way will give you the same answer, right? Because that's the work kinetic energy theorem, right? So I think regardless, we got to find our acceleration, right? So we got to do a little bit of kinematics here. So let's see, acceleration is net force over mass. So our net force is 120 newtons. Our mass is 30 kilograms. That means our acceleration is 4 meters per second squared. I'm going to not worry about the displacement. Let's go by looking at the kinetic energy. Largely just because it'll make parts B and C easier. It doesn't really matter though. So that means that after 5 seconds, our final velocity will be, well, we started at rest, VI, plus A times T, right? 4 times 5. So our final velocity is 20 meters a second. So our change in kinetic energy, well, that's KE final minus KE initial over time. KE final is 1/2. The mass was 30. The velocity is 20. Don't forget to square it. Minus our starting kinetic energy is 0, divided by our time of 5 seconds. So figure this out, and you end up getting a number that is written on this other page over here. It gives you 1,200 watts. Okay, so that's the average power that Roy was generating, 1,200 watts. All right. So let me do this. Oops. Insert blank page. Let's go dual page. All right. So to do part B, it wants to know what the instantaneous power is after 2 seconds. Well, instantaneous power is force dot velocity, right? So the only way that I can figure that out is to find the velocity after 2 seconds. Well, if we're accelerating at 4 meters per second squared, then after 2 seconds, the velocity would be 4 times 2, right? So 8. So our power here is our force, which was 120 newtons, times our velocity, which is going to be 8 meters a second. That gives you 960 watts. All right. Then part C wants to know the power after 4 seconds. Well, that will have given me more time to accelerate, right? So it's the same process, but just we're moving faster now, right? We're still pushing with 120 newtons, but after 4 seconds, the velocity is going to be 4 times 4, so 16, right? Meters a second. And so that gives you 1,920 watts. All right? So then D says, why is the power increasing? So why is the power increasing? Well, the answer lies in this equation right here. Our power basically is, you know, this is an oversimplification, but it's work divided by time. Your work is your force times your displacement divided by your time. Well, as you speed up, what happens is every second your displacement increases, right? So you're doing more work every second just because you're moving further, right? Because remember, the work depends not just on the force, but how far you move. And so you're going to go a larger displacement in a given time interval, even under the same force. Okay? All right, and then E says how would the problem change if the force was exerted at 60 degrees below the horizontal? Well, you just got to multiply everything by cosine of theta, right? Because your work is F delta X cosine theta. All of this would be times cosine of theta. Okay, so the angle doesn't really make it that much harder. Okay? All right, so 2 more examples here. Let me get rid of the dual page here. Let me do it. No, why does it not? Stupid smartboard. All right, let's go back to single page. There we go. All right, cool. All right, so here we've got this. An object is moving along a horizontal axis. So, number line, whatever. The kinetic energy in joules can be expressed as a function of time in seconds as, and it gives us this. Kinetic energy is 4t squared minus 3t plus 8. And it wants to know what power is generated. Well, power is the rate at which energy is transferred, right? So power is the rate at which energy is transferred. And we decided that was dk dt, right? So all I got to do is take the derivative of this. So this is the derivative with respect to time of my kinetic energy. So if you take the derivative of this, derivative of 4t squared is 8t, minus the derivative of 3t is 3, derivative of 8 is 0. So to find the power at t equals 2 seconds, just plug in 2. And you get 16 minus 3, which is 13 watts. Okay. So here you are given your kinetic energy as a function of time. What if you're given your kinetic energy as a function of position? All right. So now we've once again got a thing moving along the number line. This time we've got our mass, it's 0.5 kilograms. And now the kinetic energy is given by this, x squared plus 3x plus 2. Okay, what power is being delivered? Well, remember, power is the rate at which the energy is changing. But when we talk about a rate, we're usually talking about the rate with respect to time. So if I differentiate my kinetic energy with respect to position, it doesn't give me power. All right, so let's see, the derivative of position the derivative of kinetic energy with respect to position, that's the same as the derivative of work with respect, I guess net work, I should say, I'm being a little sloppy, with respect to position. And we learned that's force, net force, okay? So to be clear, where did you see that? That's from way back here. Okay, force is the derivative of work with respect to position. Or, holy cow, smartboard. Or net force is the derivative of kinetic energy with respect to position. Okay, so, all right, so why does that help me? Well, we're trying to find power. And we just learned that power is force dot velocity. Okay, so I need to find my force, I need to find my velocity at x equals 3. Okay, so let's see. So my net force is going to be the derivative of the kinetic energy with respect to position. That's the derivative with respect to position of x squared plus 3x plus 2. So that's 2x plus 3. So our net force at a position of, 3 meters, wrote 2. Well, that's 2 times 3 plus 3, which is what, 9 newtons? Okay, so cool. Now I know how much net force was acting on the object. Now we got to find the velocity. Check it out. Kinetic energy is 1/2 mv squared. So my kinetic energy, when I'm at a position of 3 meters, is determined by this equation, right? So let's see, 3 squared plus 3 times 3 plus 2. So 9 plus 9 plus 2, oh, that's 20 joules. So then I can find my velocity. What's the mass? 0.5? So square root of 80, right? All right, I don't know exactly what that is. It's right in the neighborhood of 9 meters a second. So we're going to just call it that. It's a little bit less. Oh, and so I think we're done now, right? Because now we can just go, where was it? Oh, here we go. There's enough room right here. Power equals force dot velocity. Well, our force is 9 newtons to the right. Our velocity is 9 meters a second. To the right, do I know? So that's going to give you 81 watts. How do I know what direction it is moving in? I guess I don't really. Could be going either way. Oh, shoot. I'm going to pause for 1 minute. All right, sorry about that. Yeah, we don't necessarily know the direction of motion, right? Because KE is 1/2 mv squared. So it could be moving either way. So this is either positive or negative. I don't see that being a thing that would come up. All right. But I like this example for a couple of reasons. One, it shows you how you can use your kinetic energy to find your force, which we did down here. It shows you how you can use your kinetic energy to find your velocity, positive or negative, right? And you take that square root. And then obviously you can use that to get the power. Please, 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 to quickly summarize, watch out. Power is the derivative of work with respect to time. Force is the derivative of work with respect to position. Don't mix them up. All right, there you go. Have a good day.